Good afternoon, everyone. Welcome to LEED Commissioning, Lessons Learned by a LEED Commissioning Agent, presented by Kimberly Dickey and brought to you by Green Building Research Institute. Today's course is led by experienced commissioning agent Kimberly Dickey, principal of KD Designs. This course will discuss the experiences and lessons learned from commissioning different project types. Both a large chain store project and a small local government building will be highlighted to demonstrate the shared and unique commissioning aspects of each. Here you'll see photos of our team and contributors. At GBRI, we pride ourselves on the diversity of our instructors and all of our course content.
I am Kimberly Dickey, instructor for today's course. I'm a Legacy Lead AP with a specialty in BD&C. I am owner of KD Ecotistical by Design, and I'm also the Energy Manager for the Iowa Army National Guard. I'm a GBRI LEED education provider. I provide owners with LEED project administration and commissioning. I am also a sustainable landscape designer, and as board president of the Iowa Renewable Energy Association, I educate people about renewable energy systems, investments, and the return on their investments. Let's get started. Commissioning and commissioning agent goals. Across all project types, commissioning goals are relatively similar in scope. It's a process of verifying and documenting installed systems to meet the owner's requirements and comply with the basis of design and design documents. Other goals include preventing and eliminating problems before they start during design, construction, and post-construction, before and after occupancy. This is the optimum time to deal with them inexpensively. Another goal is to lower overall operational costs for the owner. And lastly, to document and set up systems for continuous recall and improvement long after construction has ended. The commissioning process assumes accountability of all project participants, owners, designers, contractors, operators, and maintenance professionals. The commissioning team deploys methods and tools predominantly through random sampling of work product, which verifies that project delivery meets owners' project requirements. The process is ideally adapted from procedures from ASHRAE Guideline 0-2005 and Total Building Commissioning Process as defined by the National Institute of Building Sciences in its Commissioning Process Guideline O. The procedures, methods, and documentation requirements in this guideline and approach address each phase of project delivery from pre-design through occupancy and operation. Commissioning process is a process to deliver a comprehensive, uniform, integrated, and consistent approach to achieve, verify, and document key performance characteristics of facilities, assemblies, and systems. Additionally, it is to provide a specialized approach to a convergence of defined objectives and criteria set forth by the owner to the design team and installing contractors and subcontractors who are trained and apprised of their role and responsibilities to achieve successful implementation. This ensures a high-quality building product with maximum value to the owner, occupants, and users. Commissioning and the LEED rating system. Commissioning a LEED building is not just another credit in the rating system. It is a requirement. Challenges in commissioning buildings. The commissioning agent must anticipate every move of every member of the project team and every moving part of the project. Let's review specific examples where and when challenges can arise during the commissioning process. Outside air volume and controls. In terms of demand, it's important to design for code, but to limit volume introduced based on demand. In this way, you can utilize CO2 controls to limit outside air. Doing so, limiting outside air through utilization of CO2 controls, earns an extra credit in IEQ Credit 1, measurement and verification. This credit was attempted in just 2 of the 7 stores and awarded in just 2 of the 7 stores. So it's definitely an option for future design projects. The apparatus bay heat is hydronic inflow radiant heat. The heat is provided by an instantaneous natural gas water heater. This water heater also provides heat for the domestic water heating system through a closed water loop and an indirect water heater system. The base building was modeled according to Appendix G of ASHRAE 90.1 2007. The whole building method was used to compare proposed versus baseline.
Good afternoon, everyone. I'm Jessica Cabina. I'm the Education Coordinator for GBRI, or the Green Building Research Institute, and I'll be the moderator for today's course. Today we'll be presenting Green Schools Part 1, Design Elements. This is the first part of our 2-part series on green schools. The course description for today's webinar, Green Schools Part 1, Design Elements, is as follows. First, we'll go over school design, then beneficial green school strategies. Next will be beneficial green school features, ease of implementation, significance of green schools, LEED criteria, and case studies. Here you see some of our team members and contributors to our webinars. You'll also see Craig Schiller as well. He will be the instructor for today's course. Without any further ado, here's Craig.
So what makes school unique? I want to start here to orient us to what we're going to be talking about for the rest of the day. There are, in fact, several aspects that are unique to schools. First, schools have a very high occupancy rates. You have all the students during the day, all in one place, high activity, high occupancy. Second, children are particularly vulnerable to toxins and other health hazards. Part of that is their metabolism. They breathe 2 to 3 times faster than a normal adult. They absorb many more toxins, both airborne and otherwise. Finally, in my opinion, the most unique aspect of a school is that we learn in schools. That's the purpose and the function of a school. And over the lifetime of an actual student, by the time they graduate high school, they will have spent 14,000 hours in a school building. There isn't another building type where people uniformly spend that amount of time. Another unique aspect of schools is that the productivity of the occupants can be measured through standardized tests. Also, the Collaborative for High Performance Schools defines a high performance school in the following ways: that it's healthy, comfortable, efficient, easy to maintain and operate, environmentally responsive, commissioned, a teaching tool, safe and secure, a community resource, and stimulating architecture. For that reason, I'm assuming that the people taking this course have a basic understanding of the LEED rating system. It is the intention of this course not to go into detail of all the credits required by LEED for Schools, mostly because LEED for Schools is extremely similar to LEED for new construction. Therefore, I'm going to highlight some of the credits unique to LEED for Schools compared to LEED NC. Finally, let's take a look at the last 2 categories, innovation in design and regional priority. Not much has changed here. Credit 1 in ID, innovation design, is now worth a maximum of 4 points instead of 5, and they actually added a credit, the school is a teaching tool. If you remember, this is its own category, not just credit, its own category in the CHPS design guidebook, but it's just worth 1 point in LEED. Regional priority credits are exactly the same. So again, to summarize, 1 credit with a different point and 1 new credit in the ID and regional priority categories. So that pretty much summarizes the LEED for Schools guidebook. As you can tell, there is really not much difference between LEED for Schools and the LEED New Construction guidebook. So I highlighted some of the differences. I also want to highlight that LEED for Schools is a 100-point system, just like LEED NC, with 10 bonus points. The same criteria for LEED Gold Silver, 40 to 49 certified, 50 to 59 silver, 60 to 79 is gold, and 80 and above is platinum. So that concludes our section on LEED and the specifics of the LEED for School rating system. Now I'm going to focus on some of the design elements and design strategies that make up a green school. A lot of these strategies are going to match the new credits in the LEED system that we just went over, but most of them are really important to green schools regardless of any rating system. The first and the foremost important design element is daylighting. Second is indoor air quality. Third, acoustics. And the fourth design element we're going to talk about is master planning and multipurpose. So the next indoor air quality topic we're going to talk about is mold. Mold is so important, as we talk about with the health and the asthma, etc., that it is its own credit in LEED. IEQ credit 10 is mold prevention. Now, as its own credit, it does have a little weird niche. It actually requires you to hit the following credits. 3.1, which is construction indoor air quality management plan during construction. IEQ credit 7.1 and 7.2, which is thermal comfort compliance and verification, essentially ensuring that the temperature in the community is appropriate in the school to prevent mold growth. Sustainable Site Credit 10 is the Joint Use Facility Credit. That is a little more unique. As I mentioned, schools are a community-funded community service. This Joint Use Facilities Credit wants to combine more community services in the same place. For example, in this credit, this credit requires schools to have at least 3 of the following services shared by the general public in the school site. That's either an auditorium, a gymnasium, cafeteria, or another classroom, playing fields, or joint parking. So again, we're taking community services and applying them to a community service, the school. The other option, so there's 2 options. The other option for this credit is to provide dedicated space for 2 of the following within the school site. And again, they're not limited to these options. So having a commercial office, a health clinic, a community service center, police office, library or media center, parking lot, or commercial sector businesses on the school site create a joint use facility. 2 other examples. This image is one that I took in Pittsburgh for a school that has a designated farmers market space. So on their lawn, they actually put porous pavers under the grass so that farmers could come and park and have their farmers market on the school site. So that the final one, and this is the last slide I have for you. This is the school with the water cistern with the waterfall, the Chartwell School in California. I'm putting this on here because this is also part of the research. The post-occupancy evaluation and occupancy evaluations, these tell you how the students and the occupants and the teachers are doing, not just how the building and the system is doing, but how its occupants are doing. Throughout this presentation, I've talked about increased performance and increased health. Well, where does that stuff come from? That comes from research. That comes from a school being used as a teaching tool. The part of that is really important is that we can now quantify the benefits of these green schools. So if you look at this chart, the average satisfaction for this school is significantly higher than the average from an average of 158 buildings. What that means is that this means that we can start quantifying the data for green schools. I'm showing this as the last slide because this is a teaser for the next half of the course. We're going to talk about the benefits of green schools, and it's because of this research. Yeah, so I think I'll end it there.
Hello, and welcome to today's course, Geothermal Building Systems, from the Green Building Research Institute. I'm Rebecca Joan Brown, GBRI's Director of Education, and I'll be leading the course today. Please take a second to become familiar with the on-demand control panel to the left of the course slides. This will allow you to navigate between slides, pause the course, or search for specific information. There's also a tab in the control panel with a paperclip icon on it. you can click here to access printable PDFs of the note pages for this course. Today we will be discussing geothermal energy, both in terms of geothermal heat and electricity that is generated from geothermal sources. We will look at how this energy is generated and at how it can be incorporated into green building projects. We will also look at how geothermal energy is addressed within the LEED green building rating system. Geothermal energy is the energy that's contained as heat within the Earth's core. The core of the Earth is estimated to be around 7,600 degrees Fahrenheit. This heat is maintained at such a high level, rather than cooling quickly over time, because the core of the Earth contains a high concentration of radioactive elements, such as uranium. The center of the core is slightly less than 4,000 miles from the surface of the Earth, depending on where along the surface is being measured. Geothermal heat becomes less intense the closer it is to the surface of the Earth, but is still a very strong source of heat and energy. The outer 6¼ miles of the Earth's crust contains 50,000 times more energy than is present in all known oil and gas sources combined in the form of geothermal heat. Geothermal heating is considered to be a renewable resource, as the amounts that would be used for heating and energy, even on a very large scale, will not significantly affect the core temperature of the Earth. Geothermal heat also produces very few negative byproducts when used to create electricity, only a small fraction of the emissions that are associated with energy production from fossil fuel sources. Unlike closed-loop systems, an open-loop system uses well water or another below-ground water source that circulates through the system and is discharged back into the ground. A closed-loop system uses a conducting fluid that is entirely contained within the system. In an open-loop system, water is drawn up into the building from the well, the heat is extracted for conditioning, and then the water is released back into the well through an injection well to be reheated. Open-loop systems are less expensive than closed-loop systems because there is less drilling and tubing required, but they are subject to increased environmental oversight, as water is being released into wells or aquifers that may affect local watersheds. Open-loop systems are also more space-saving because they are built down rather than stretching out for hundreds of feet. There are some limitations with these types of systems, most notably that this system will only work where there is a viable well or underground aquifer that may be tapped to provide the water for the system. The second form of geothermal generation is the flash steam method. This type of system requires more heat than the dry steam system, with water that is at least 360 degrees Fahrenheit. Rather than allowing the steam itself to escape into the turbine, the actual hot water is drawn up, still pressurized, and allowed to flash into steam once it is within the generator. Although the water is hot enough to form steam underground, the pressure there is too great, and the steam will not actually form until there is space for the molecules to expand. Once the water has condensed behind the turbine, it is injected back down to reheat and begin the process over again. Our first case study is the Friends Center in Philadelphia, Pennsylvania. This 3-building complex serves as a Quaker meeting house, as well as office space for over 20 nonprofit organizations. The building renovation was completed in 2009 and earned LEED Platinum certification. One of the developments that allowed the project to earn this certification was the geothermal heating system that was installed. While the initial costs for this system were high, especially because of the dense urban location of the existing building, the geothermal heat was found to have significantly lower operating costs than a traditional HVAC system and provided an estimated payback time of 7 to 15 years, which the Friends Center was willing to take on. Thanks for joining us today for Lessons Learned from 99 LEED Projects, Indoor Environmental Quality. I'm Rebecca Joan Brown, and I'll be leading the presentation today. There will be a short quiz at the end of the presentation, and you'll need to score 80% or greater in order to get credit for the course. You may take the quiz and watch the presentation as many times as you would like. It is also not necessary to finish the course all at once. You can start now and finish later at your convenience. Lessons Learned from 99 LEED Projects is a 6-part series that looks at 99 LEED Gold and Platinum certified projects to identify what strategies work best and are most popular in each of the 6 LEED categories: sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environmental quality, and innovation in design. We will look at strategies implemented from the 3 major LEED rating systems and discuss the most frequently applied strategies, those that are easiest to implement, and those that stand out as especially unique or elegant solutions. This particular course provides an in-depth look at the importance of improved indoor environmental quality. We analyze the strategies that our 99 projects implemented to improve the indoor environmental quality for building occupants and highlight some of these strategies through case studies. According to the U.S. Environmental Protection Agency, the average American spends about 90% of their time indoors. It's been widely publicized that indoor air is often more polluted than the air outside, and because of this concern, many builders, designers, and building managers are working to find ways to improve indoor air quality. The most common indoor pollutants include VOCs, mold and mildew caused by excess moisture, combustion products, dust particles, bacteria, and viruses. Many of these problems are especially common in older buildings, which may contain now banned products and outdated ventilation systems. Asbestos installation, lead-based paint, and paints and adhesives containing other toxic substances are some harmful products that may have been used in older buildings, but are now banned or discouraged for new buildings. Poor indoor air quality is a primary cause of sick building syndrome among building occupants. Sick building syndrome is a term used to describe acute but broad symptoms, such as headache, fatigue, or nausea, that are associated with a building or space but have no precisely defined cause. These types of symptoms can be worse for children whose school environments are more polluted or not well ventilated. According to the Center for Disease Control and Prevention, adverse indoor air quality contributes to more than 14.7 million sick days in schools each year. Healthy air is important for everyone, but in particular for people with allergies, asthma, or other respiratory problems. Apart from staying healthy, better indoor air quality enhances occupant performance and productivity, reduces environmental impact, and decreases the likelihood of liability and litigation issues. Some of the more common daylighting strategies that we saw implemented in our 99 projects were the use of the sun path diagram, functional layout of building spaces, and the use of atriums. Sun path diagrams show how the sun will be positioned throughout the day on a site, and designers can use this to orient the building to take advantage of light and shade as they exist on site. This will generally mean orienting the building along an east-west axis so that the longest sides face north and south. Sunlight from the east and west will be very intense in either the morning or the afternoon, and can cause glare from heat gain, particularly from the west. Light from the north is ample and indirect, so windows along the northern side of a building will allow in light without glare or heat gain. For the better part of the day, the sun will shine from the south, so windows along this side of a building will get excessive sunlight, especially during the winter when the sun is at a lower angle and may shine in more directly. Designers should be careful to harness this resource carefully, applying shades and screens to prevent glare, and accounting for potential heat gain, either through the inclusion of a thermal mass or by choosing windows that will reflect the heat and provide adequate insulation. Related to building orientation is the layout of spaces within a building. Consider the function of each space and place it accordingly. Rooms that are frequently occupied could be placed on the north and south sides of the building to take advantage of natural lighting, and spaces that are not occupied frequently, such as storage spaces, could be located in areas that will not receive as much light. If a space will be primarily occupied at certain times of the day, it may be located using this as a factor as well. An example would be an after-school program space that could be located on the east side of a building, since it will be primarily occupied in the afternoons. A primary source of the building's daylight is the central atrium, which allows natural light to pass into workspaces on the open plan floors. The skylights that feed the atrium are louvered to mitigate light intensity and to prevent glare. Reflective aluminum panels along the floors that border the atrium create a light wall that works with the chandelier to further reflect light into the space. The Empire State Building is in the process of completing some major green upgrades, and the project is aiming for LEED EB certification. As one of the most recognizable buildings in the New York skyline, its sustainable aims are sure to influence other projects. One project improvement is the installation of approximately 6,500 thermopane glass windows. The team used the existing glass and sashes on site to create triple-glazed insulated panels with some new components that dramatically reduce both summer heat gain and winter heat loss. The windows were created on-site from the existing glazing. This enhancement optimizes IAQ by keeping occupied spaces at comfortable temperatures and also improves the energy performance of the building by reducing the thermal loads that are required. Other IEQ-specific strategies that the project employed include implementing an IEQ management program, providing daylighting and other occupancy controls, and introducing demand-controlled ventilation. Hello, and welcome to the Green Building Research Institute's residential series, The Elements of a Green Home. Many philosophies around the world believe in a classical set of elements that are believed to form the simplest essential parts that make up everything on Earth. The most widely held theory of classical elements is that there are four: earth, water, fire, and air. Some cultures include a fifth element called space, idea, spirit, or void. We define an additional sixth element as the built environment, the combination of all other elements into a man-made structure. In this series, we would like to talk to you about how these 6 elements play a part in sustaining your home. We've organized this 6-hour course into 3 2-hour courses that represent the elements: sites and energy, representing the elements of earth and fire, water and materials, representing water and the built environment, and IEQ and innovation, representing air and idea. We hope that you will find all of these sessions informative and come away with some great ideas for greening your residential projects. Today is our first session, where we will be focusing on water and materials. This course will include discussions related to the importance of green homes and the current drivers promoting design and construction of green homes in North America. We will discuss strategies related to water efficiency and material selection that can be applied to the design, construction, and management of a home. We will link each of the strategies discussed to applicable LEED credits available under the LEED for Homes rating system. A LEED case study will be discussed to analyze the execution of the strategies we discuss. A green home is one that is designed to be environmentally friendly and sustainable. Green homes focus on the efficient use of energy, water, and building materials, and on doing no harm to their local and global environments. Green buildings and homes are often certified by third-party rating systems, and each system uses its own criteria. Some examples of green home certification bodies include LEED for Homes and the National Association of Home Builders National Green Home Certification. Owners of green homes not only save energy and reduce their environmental footprint, but can also realize many other benefits. Green homes generally have lower operating costs from energy and water bills as a result of improved efficiency measures. As green home building has become more mainstream, there are more federal tax credits and local government and utility company incentive rebates available, providing financial incentives for building a green home. Green homes are also healthier for occupants because of improved indoor air quality, less harmful off-gases, and prevention of water intrusion, which can create mold. If your green home is certified, it will often have a higher value than a comparable standard home, and it's much easier to market the benefits of the home to buyers. Green homeowners are also generally seen as more involved in the upkeep of their home, and having made green improvements will show potential buyers that the home has been well maintained. A green home will have less maintenance and repairs because of the increased useful life of sustainable products and materials, and this will in turn result in cost savings. For example, a properly planned landscaping system will reduce the amount of time spent maintaining the yard, minimize the water consumed, and reduce the need to replant as often. As you can see from this slide, there are many benefits to building green. In the United States, there are various codes that prescribe how homes are built. There are many reasons why building codes exist, but primarily they specify the minimum acceptable level of safety for the built environment. Building codes protect public health, safety, and the general welfare of the citizens that occupy these structures. However, building codes fail to adequately address sustainability and the relationship of the built and natural environments. A code-built home meets the minimum requirements as set forth by the government, whether state or local. When builders exceed code, they often see a dramatic increase in energy savings and will typically notice a drop in carbon production, water use, and waste production as well. This graphic shows the water savings you can get from replacing different older toilet models with water-efficient low-flow toilets. If toilet flushing accounts for 26.7% of your indoor water use, and you replace a 7-gallon toilet with an efficient one, this will work out to a 20% total reduction in your indoor water use, which can be pretty significant. As our population grows, our cities expand, and the amount of waste we produce balloons, managing waste is becoming a greater challenge. Luckily, there are several alternatives to the less eco-friendly methods of landfill and incineration. Reducing the amount of trash we produce, extending the lifespan of products, reusing materials, and recycling our waste into new products are all key components of modern waste reduction and play a critical role in the reduce, reuse, and recycle waste management triad. More and more cities are offering recycling programs, and some offer curbside pickup and sorting. Typically, these systems accept glass, paper, plastic, aluminum, and cardboard. Recycled products can often have the added benefit of reducing air pollution from the incineration of garbage waste, reducing water pollution from landfills, and reducing the costs and impact of conventional waste disposal. For LEED for homes, construction waste management is covered under MR Credit 3, Waste Management. This credit does include a prerequisite for which you must investigate and document local options for waste diversion from the home and document the diversion rate for the construction waste. Once this is done, projects can earn up to 3 points for construction waste diversion through either reducing waste to less than 2.5 pounds per square feet or by diverting 25% or more of total project materials away from landfills and incinerators. We will return to Eaton Street for our materials case study and look at how the project made good use of materials and practices. The project earned 9 of 16 possible points in the Materials and Resources section for LEED for Homes. Best practices begin in the early stages of design and construction. The aggregate for the foundation was locally produced, and the building pad was made from reclaimed material from a local road project. The concrete for the foundation contains 30% fly ash, which is a pre-consumer recycled material. For the building's framing, wall, roof, ceiling, and floor components were fabricated off-site, which prevented enough waste to eliminate the need for a 140-yard dumpster on the construction area. The studs used were made from recycled wood from local lumber mills.